All right, so for several episodes now, we've been looking at solving Poisson's equation, where you have your Laplacian of the electric potential is given by the negative of the charge density. We got a pretty good idea now of how to work with this thing. We've done several problems with it. The question becomes, where does this rho actually come from? There's really two options. One is you can take charges and just glue them into place. The other option is something called polarization. So here's kind of the picture you want to have in mind of polarization, okay? So let's suppose you've got a piece of material. Let's suppose you've got a rectangle of material that has some electrons in it that are kind of free to move around, right? Not entirely free, it would be a conductor, but they're a little bit free to reorient themselves. What you do is you create an external electric field, right? So this is something you turn on. You place two leads across here. You apply a voltage. You turn on an electric field. What's going to happen is that the negative charges are going to move against the field, right? So you're going to have a buildup of negative charges somewhere down here. They're not going to all immediately, drop to the end because they are negative charges. They will repel each other. But because you've got a little bit of adjustment of negative charges moving down, they leave behind a few positive charges up at the top. Now, if this were a plasma and you could have positive and negative charges moving, that would be, it gives you the same picture. But for most applications, we're talking about solid material where it's the negative charge that moves and it leaves behind positive charge. But it doesn't really matter because you end up with the same picture either way. And so what happens is you have a charge distribution, right? This gives you a charge density here. But they can't leave the shape, right? They can't just leave the object. I mean, they could if you ramp up the electric field high enough. That's a different problem, though. But they can rearrange themselves, but they can't leave. So we call these things bound charges. And it turns out, when you work out the math on this thing, the bound charges can end up in one of two places. They can either end up inside the material, in which case you have a rho bound charge density. So this is the interior bound charge. Or you can have some charges end up along the edge. So you might end up with a specific set of charges that end up along the edge of the material. We call that one sigma b for the surface. So this is the exterior or the surface bound charge. Again, none of them can leave the shape. It's a question of whether they're inside the bulk or whether they're there along the boundary. So this creates two charge densities that we have to keep track of. So this rho is now going to be a combination of rho bound plus sigma bound. And this one is charge per unit volume. This is charge per unit area. So we'll have to do something with this here. We'll just basically have to divide it by a dx in order to get the units to work out. Because that's the thickness of the layer that it's living at. And so basically we have to figure out what these two things are, where do they come from? It turns out you can calculate something called the polarization vector. The polarization vector is going to go from the negative charge to the positive charge. That's different than how we usually do an electric field. It's opposite intentionally. The polarization vector is defined as going from the negative charge to the positive charge. If you've had a chemistry class, you can think of this as your dipole vector, right? So if you think of this as like a water molecule where you have a little bit more negative charge on one end and a little bit more positive charge on the other end, this is going to be that electric dipole going from one end to the other. And it turns out both rho b and sigma b are directly based on the polarization vector that you set up. So for inside, your rho bound is going to be a negative divergence of the polarization vector. So this assumes, this only comes into play if your polarization vector has a spatial dependence, if it changes from one end to the other, because if this thing is uniform, you're not going to end up with anything interesting because divergence of a uniform field is 0, right? On the other hand, your sigma bound, you almost always get a sigma bound. This is going to equal the polarization vector dotted with n hat. And you say, well, what's this n hat thing? N hat is the unit vector that's perpendicular to a given edge of the shape. So for example, on the bottom, your n hat is going to point this way. On the top, your n hat is going to point this way. On the left side, your n hat is going to point this way. And on the right side, your n hat is going to point this way. So you actually get a different row bound for each side of the shape. Right? So for each side, it's going to be a different thing. So if it's a rectangle, it'll be 4 vectors like that. If you use a circle, let's suppose you polarize a circle, right? Then your n hat is continuously varying around, right? You have to use an r hat vector to describe that. Right? Or if you made it an ellipse, n hat's going to get even more complicated than that. So before you start the problem, you have to figure out what your n hat is all along the edge of your shape. So the way you solve this problem is you start with the polarization vector, right? You're given the polarization vector and the shape. You use that to get row bound and sigma bound. Then you can take those, feed them into our machinery here that we've already got in place, and that will give you phi, which will give you the electric field. So what we're going to look at in this video is a code that will take us from the polarization vector through these 2 steps to finally get the electric field for a polarized object. So we're going to start out this notebook by defining the geometry of the polarized object. And in order to do that, we're going to use the Shapely library. Shapely is a popular, useful, versatile library that allows you to work with polygons and different shapes in Python. I've got some instructions up here about installing that if you're in Anaconda. You can do something similar if you're in an online Jupyter Hub like I am right now with installing it through pip. But basically, you first want to get the Shapely library. It's pretty easy to find. We're going to import a few things. We're going to import point so that we can have a single point location in space. We're going to have polygon, that's going to be our shape, and we're going to have line string. So in order to specify our charged shape, we need to specify what the corners are of the polygon. And in this case, we're going to have one corner at 1, 1. We'll have another corner at -1, 1. We'll have a corner at -1, -1, and a corner at 1, -1, which is going to make us a square. So if you want a more complicated polygon, you just add in more points. We'll try something a little more complicated later. And then to create our shape, we just use the polygon function of corners. So corners is a list of x and y coordinates, and then polygon takes that list and creates a Shapely shape from it. And so this is all the information we need to know about this shape. So just to give you an idea of how this works, I've created a point here. So a point just is just one of these dots. So we've made a point 0.9 and 0.5. So that's going to be not quite all the way to the right and about halfway up. So our new point is let's get that a different color. Our new point is going to be somewhere over here. And just to give you an idea of how this library works, we're going to be using the within function. This asks Shapely whether the point P1 is within the shape that we created, right? So is P1 inside the bounds of shape? And it's going to print true or false. It prints true right here because, of course, this green dot is within the red shape. And that's going to be important later because we want to be able to tell whether the point we're at is within the polarized object or outside the polarized object. It can also tell you whether 2 shapes overlap. So for example, we make a second polygon. Let's make this one blue with corners of -1.1 and 0.6. So we're going to go over here and down this much to about here. We're going to take our second point at -1.1 and 0.7. So we're going to put that up here somewhere. Then we're going to go to -0.9, so about here, and 0.7. And then we're going to go down to -0.9 and 0.6 Put that about here. Oh, this is supposed to be a positive points. It's not going to negative 0.6. Well, just imagine this one scrunched up a little bit. So I have my P box here is the blue shape. And so P box dot overlap shape tells me whether the blue box here overlaps the red shape. And of course they do overlap, and I get a true here. That's also going to be important because we want to be able to tell whether our grid points are along the edge here, right? So remember, we are approximating our space here as a grid of points coming along here. And I want to be able to tell, is a grid point within my polarized object? Is it outside my polarized object? Or is it kind of close to the edge of the polarized object? Because I'll need to treat that a little bit differently. So that imports the Shapley library, gives you an idea of how that works. In our next cell, we're going to define the polarization. Now, polarization, in your textbook, it's written as a vector, but you have to remember that it's a vector defined within a region, right? And so we first have to ask ourselves whether we are within the shape, and then we return the polarization vector if we are, and we return 0, 0 if we're not. Remember, the polarization vector, it really only exists inside the shape. Outside the shape, it's 0, 0. Right? So inside our shape, in this case, we're going to have a polarization vector pointing straight up because we're going to have 0 x component and 1 for the y component. And so we take our input coordinates, x, y. This is the point of the grid that we are sitting along right now. We create a point here and we just ask, is that point P within the shape? And if it is, we have a polarization vector. If not, we got a polarization of 0, and we just return this vector back to our main code. So we're going to define that polarization vector. In our next cell, we have the exact same stuff that we have been working with before, right? We set up our boundary conditions. We're going to set those to 0 for right now. We have our bounds here. We're going in a square from -2 to 2 on each side. The part that's different is how we evaluate rho, right? Because now we don't just set rho to whatever function we want anymore. Now rho is determined by the polarization vector, right? So our rho bound, we need to calculate this thing. So rho underscore b is going to be our bound volume charge density. This is the negative divergence of the polarization. So we're going to start out with all zeros here. And you might remember that NumPy doesn't have a built-in divergence, so we're having to do the divergence on our own here. And so we loop over all of the points in the grid. We establish what position we are at. So here's our position vector. And we look at a small box around that position vector. Remember, we want to be able to tell whether we are overlapping the edge, because we want to be able to tell, is the spot I'm at anywhere near here? Because when you think about these grid points, we're dividing the grid up into boxes, and so we want to tell whether the box that we're currently in it overlaps with the polarization area. And so we just check for if P dot within shape, right? This is the shape that we defined earlier. So we ask ourselves if P is within the shape, then we go about setting up our rho bound here, right? So we take our x point to the right, our x point to the left, our y point above, our y point below, and we calculate our divergence. So we calculate dBx as our polarization at each of those points. We're taking the x component minus the x component, then our polarization at the point above and our polarization at the point below. We're looking at the change in the y component. And then here's our familiar divergence calculation that we've already used before. So it's the derivative with respect to x of the x component plus the derivative with respect to y of the y component. We're dividing by 2dx because that's how far we are stepping. We're stepping a point to the right and a point to the left, a point above, a point below. That's a net of 2dx in each direction. And we put a negative there because that's what we need for this charge density to work out. So that's if the box is within the shape. So if our box is entirely within the shape, then we can just move along there. Otherwise, if our box overlaps, so the central point is not there, but there's a tiny
fraction of it. So this is if we are on an edge. This is when we're going to start looking for the surface charge density. So remember, our rho bound is negative divergence of the polarization. Our sigma bound, our surface charge density, is the polarization dotted with n hat along the border. So in order to get that, we have to first calculate n hat. And so the way we're going to do that is looking at defining the edge. So this is where we create a line going along the edge here. So we've got the shape exterior coordinates of k and k plus 1. So we're looking at, is this thing pointing left and right, up and down, or something else? So this is looping along each edge of the shape. So then we're going to use this disjoint function, and disjoint simply says these two shapes have absolutely nothing to do with each other. So the P box and the edge don't touch at all, like the P box is not along this edge. So we're looking for whether they are not disjoint, meaning whether they do touch. Then we know we found n hat, we found the edge that we're interested in. So remember, we've got a box here. When we're looking at one of the points along our grid, we have to figure out which edge we're next to, right? So this point is not along the top edge, it's not along the right edge, it's not along the bottom edge, it is along the left edge. So we would say that these three edges, the top, the right, and the bottom, are disjoint from the dot here because they're nowhere near each other. They don't overlap at all. Whereas this dot, if I draw a little box around it, that's what we mean by P box, it's the box around the point, it does overlap this line right here. So when we're working with lines like that, we have to use this disjoint feature here. So if they are not disjoint, which I guess would mean they are joint, then we're able to calculate n hat, right? So our n hat here is going to be pointing perpendicular to here. And so in order to get that, we use this little construction where we've got shape dot exterior dot coords k plus 1 of 1. And you notice here, basically, we're swapping the x and y in order to make it perpendicular. So for along that left edge, I want the thing to be pointing out this way to the left. And so I want to swap my y and my x because the thing is changing along the y, but not along the x. So that's going to give me something pointing perpendicular to the edge itself. And then here we just add to our row the dot product of the polarization with n hat, right? So that's our dot product there. Notice we're combining sigma b and rho b. I don't have a sigma b defined here. I just have the rho b because it's only rho bound that shows up in Poisson's equations. We're kind of combining them together so that we've got this as a rho b, meaning it's a very thin rho b. So we're taking our surface charge density as being a very, very thin volume charge density. So that's what we have to do to get rho set up. Rho is a much more complicated process now, but we don't actually have to touch this part again. This machinery will stay the same. It's really only the polarization area and vector that will change in the problems that we work. And then here we come to our familiar finite differences machinery. We are looking to converge upon our potential difference not changing more than the target accuracy. Here we've got our finite differences here. Here, rho bound is where all of that stuff goes into play. So let's run this and take a look at our results for this polarized square. Right, so we've got our four edges along the x-axis and along the y-axis. Let's get a little bit better angle to view this from. So you can see this is giving us the direction of our polarization, right? We've got our polarization along the y-axis. It's coming back all the way up here. Inside this square, we have a square here. Inside that square, our polarization is pointing straight up. So when I come down here, that's the direction we get here. We've got negative charge accumulating one side, positive charge accumulating on the other. So we have a trough in the electric potential and a peak in the electric potential. Let's see what that looks like when we calculate the thing's electric field vector. Again, we're using the same machinery that we used before to calculate the gradient of this thing. So you can see that inside the square here, we end up with electric field coming out of one side. So we've got positive charge along this edge. We've got the electric field going into this side. So we've got negative charge along this edge. And so what you see is we've got a discontinuity in the electric field along the edges where we have the charge building up, right? So along this edge, there's a discontinuity because down here, we've got a electric field pointing down. Here we've got electric field pointing up. Here we've got down, and here we've got up. So you have a discontinuity anywhere you accumulate surface charge. We don't have a discontinuity along the left and right edges because there's no surface charge that builds up along there. Let's see, let's try out our quiver plot. Oh, there you can really see this going on where we've got our regions of positive and negative charge along these edges here. And then we can calculate the divergence. This should give us back the charge density. Sure enough, we are building up positive charge along one edge of the square, negative charge along the other edge. We don't have charge anywhere else. We don't have charge outside of the shape. We don't even have charge inside the shape because this polarization vector is uniform, so it doesn't have a divergence inside. We're really only getting the surface charge density at the top and at the bottom there. Now comes the fun part. We should be able to calculate the total charge distribution, right? So if we take all of those little pieces of row bound and add them up at each spot, these two should cancel out because there's no total charge, right? The idea of a polarization problem is that you start with an electrically neutral piece of material. You induce a polarization so that you are shuffling around its charge, but you can't ever add charge or take it away. If we run that, lo and behold, we get a total of 0. So unless you have excess charge that you've added, this total should always come out to be 0. Now the fun part comes in where we can change the geometry that we have. So let me save a copy of this. We're going to call this one 5A, and we're going to do a polarized circle. In order to do this, I need to change my polygon here to be a circle. So I'm going to paste in a little code snippet that I pre-wrote for this. So we're going to define a radius of 1. We're going to have 100 points along this circle, and we're going to slice the circle up into 100 angles, going from 0 to 2 pi. And basically, at each one of those angles, we're going to append a point along the circle of cosine A and sine of A, both times the radius. That's how you parameterize a circle. Now, really, this is not a true circle. It's a 100-point polygon. But you can approach a circle by making this number higher and higher. There we go. And then we'll define our polarization. Let's use the same polarization vector that we had before. The difference is this time our geometry. So we're going to leave our polarization vector at 0 and 1, and we're going to change our geometry. Now I have to rerun this piece here to get my new row bound. And then we'll run our code here to get out our electric potential. And you notice it's quite similar to what we had before. The difference now is that this feature is kind of getting extended around the edge of the circle there. Let's take a look at our change that pops up here. Yeah, you notice how it's curving around a little bit more. There's not this nicely defined cutoff of where you have charge and where you don't. You really only have it going to 0 here at the equator there. Let's get our electric field up. Let's see. So here we have our box, right? So we have these two well-defined edges. Now we're going for a circle instead. And you can see now that boundary has changed. We've got a circle being drawn around here where we have the discontinuity instead of those two well-defined edges. So we have this kind of uniform electric field on the inside, and then we've got this thing coming around here. So this we could use, for example, to model an electric dipole, because we would have the electric field going out of the positive edge and coming into the negative edge. Let's take a look at that quiver plot. Always interesting to look at. Oh yeah, this is looking groovy here. This is great. So we've got electric field coming out of one edge, going into the other edge, and we have these 0 points along the sides there. And then let's check our charge density. Here you can see that we get the charge density only along the perimeter. So even though our first example was a square and this example is a circle, they both have the common feature that they've only got charge building up along the edges because that polarization vector inside is uniform, even though the distribution is different. And then let's check our total charge. Okay, good. That should come out to 0.0 there. All right, I want to look at one more polarization vector. For this one, we're actually going to go to Griffith's textbook, Introduction to Electrodynamics. I'm looking at problem 4.10 in the 4th edition of this textbook, where Griffiths wants us to look at a sphere of radius r. Well, I already have a circle set up, so we'll use the circle as a proxy for the sphere, with a polarization vector of P of r equal to kr, where k is a constant and r is the vector from the center. So we're going to keep the same geometry we have here. We're going to keep the same circle. But we're going to come down here, and instead of a uniform polarization vector, we're going to have the position vector. So we're going to have k times x for the x component and k times y for the y component. So this thing is going to point along the radial direction, and it's going to get bigger as we go out along the radial direction. Now I will need to define k. He wants us to leave it as generic. We're just going to set it equal to 1 for now. And obviously, we can scale the problem with k if we need to. So what he wants us to do in this problem is calculate the bound charge densities, sigma b and rho b, and then find the field inside and outside the sphere. So you can solve this analytically. You're probably required to in your E&M class, because this is a great problem to give, but I want to solve it computationally. So I've put in to our machinery Griffith's two conditions: that we have this circular region. I mean, you can imagine what will happen with a sphere. It's just going to rotate around the extra axis. We've defined our appropriate polarization vector, and now let's run our finite differences code and see what we get for our electric potential and electric field. And there we have it. We get this rather interesting looking electric potential where it is sinking down in towards the center. We expect it to have a nice radial symmetry because of how we are, expanding out from the center. I don't think rotating is going to give us too different of a view. Yeah, we're looking at a corner instead of an edge now. You get the idea. Let's take a look at the electric field. That's what Griffiths wants us to get from here. So we'll calculate and then graph our electric field. And this part is really cool. I don't really notice the discontinuity anymore. There might still be one depending on what the surface charge is doing. We'll have to look at the surface charge. But yeah, everything points inward toward the center, which is really cool. Let's see. Here's another way. Let's get the quiver plot. Yeah, it doesn't tell us anything different there. And then we'll take a look at our charge density. And what you notice is we get this crown of positive charge along here. I would like to tell if there's anything going on the interior. Let's take a look at it from a 90-degree angle. Okay, yeah, so we are getting negative charge on the inside, it looks like, and positive charge on the outside. If we go to negative 30... Yeah. So what you can see here, we're getting a negative charge on the inside. It looks like it's even a negative uniform charge. Which does make sense because you would be taking the divergence of r, which is going to give you a uniform scalar, and then we're getting the divergence here. Now, anytime you have these polarization problems, there has to be a positive and a negative bound charge because the total has become 0. And speaking of which, let's calculate our total charge. Ooh, dear, that does not come out to be 0. I suspect we've got a little bit of rounding error there. I'm guessing that's just some, even though it looks like a high number, I'm guessing we've got a little bit of rounding left over there. So this is a neat way of looking at these polarization problems. You have to do a lot of these in an undergraduate E&M class. And so I hope this machinery is useful to you, giving you another way to come up with the answers to these, visualize the electric fields, and confirm the analytical results that you're getting. And then, of course, being able to solve problems that you couldn't be able to solve analytically. I think that wraps it up for our discussion of electrostatic fields. So in the next video, we're going to start taking a look at magnetostatic fields, where we'll get to have some curls and stuff flying around and curling around. So it'll be a lot of fun. Thank you so much for watching. I'll see you next time. Bye-bye.